We're Team Cherry Blossom, and this is our video for the group project.
Hi, I'm Tanay. My roll number is 21005015.
My name is Amya Deshmukh. My roll number is 21005001.
And my name is Harsh Punia. My roll number is 63. Okay, our topic is memory hierarchy optimizations for graph analytics. And so the goal of the project was first to experiment and tinker with various cache hierarchies using the simulator ChampSim. We tried out various cache replacement policies. We tried out cache inclusion policies, and we tried out different sizes of the caches, and we compared them with the baseline. And second is we try and explain what the results are in the context of graph analytics. We use traces such as the shortest source shortest paths, breadth first search, and others. So this is an overview of the cache inclusion policies we implemented. By default, ChampSim comes with a non-inclusive cache policy. What that is, we'll explain in a minute. This is the schematic image for the inclusive cache policy. What happens in an inclusive cache policy is that a block that is in a higher level cache is present in all the subsequent lower level caches. That is, a higher level cache is always a subset of the lower level caches. So cache fill by default happens like that. When you have a miss in the higher level, what you do is you fill up all the lower levels below it, and then it gets filled up in the higher level. So we didn't need to change anything for that. For invalidation, if a block is evicted from a lower level cache, it has to be invalidated in a higher level cache, because then the subset relation won't be maintained.
So I'll explain the exclusive cache policy. So in exclusive cache policy, we enforce that every block which is present in the higher level cache is not present in the lower level caches. So for example, if L1 demands some block X, then it is first brought to L2, but it isn't stored in L2. It's just sent to L1. As a result, it only appears here. Secondly, if some read misses in L1, again the same thing happens. It's installed only in L1. And in case of eviction, unlike an inclusive policy, what we do here is once we evict a block from L1, we send it down to L2 and store it there. So again, the subset relation is maintained. So that's an overview of the exclusive cache policy. So again, in this policy, a block is present only in one cache level at a time. And this explains the eviction, which I just explained. So the other thing is when a lower level cache, for example, L2 gets a cache miss, it requests the memory from the DRAM or the main memory. And instead of storing the block, it again just passes it to the higher level cache. And this is the write back. So yeah, that takes care of the hierarchies.
Okay, now I'll explain the cache replacement policies. There are many cache replacement policies, but we mainly focused on the ones which we implemented for the Lab 5, and we implemented a couple more here. The first is the first in first out and the last in first out cache replacement policies. Both of these are queue based policy, which are basically first in is whichever block was first entered in the set, that's the one which is evicted first, and last in first out is whichever the block was last entered in the set, that will be evicted the first. The recently based use policies are the least recently used and most recently used policies. Least recently used policy indicates that block which was used the last in time, that was least recently used, will be evicted. And most recently used policy indicates that the block which was just used, like most recently used, that will be evicted in a set. And then there are other policies. The basic is the random policy, that any block can be evicted from the set with a random probability. And for the frequency, we implemented the least frequency used policy, which basically means that we store the frequency of how much ever a block is used in a set, and whichever block has the least frequency, that is the one that is affected. So, as in our project goal, we also had to focus on different cache hierarchies. One aspect of that is adjusting the cache sizes. So basically, what happens is when you increase the cache size, the latency of the cache works, but the number of misses tend to go down because there is a higher chance of the tag matching. So what we did was we increased the number of sets in a cache to see if that would help with a better hit rate. But we made sure that the ways were kept constant, because that led to easier tracking in between the different sizes.
And the other thing that we did was we maintained the thing which Taneja said, ki as we increase the cache size, we made sure to increase the latency in a feasible manner. So the trend of that increase we took from a paper which was given as a reference in the Google Doc. So we used a similar trend in the latency. So yeah, that